Continue. I have to type myself continue.
Yes, yes.
Okay.
So yeah, welcome back everybody for this new session of the Cardiff Analysis Seminar. Today is the last seminar before the Christmas break. So we will then stop for 4 weeks and we will be back on January the 11th for the winter season of the Cardiff Analysis Seminar. But today we are delighted to have Monique Dauge from Rennes, who will talk about whispering gallery modes in radially symmetric micro-resonator, asymptotic analysis and numerical computation. So Monique, please.
Thank you, Matteo. So I am delighted to talk in Cardiff without traveling more than my home. So what I will talk about as its origin in physics, in optronics. And so it was the opportunity of developing mathematics at the theoretical level and also computing and coding. So I want to tell this story this afternoon. So you see, it's with Zoïs Moitié. So Zoïs Moitié is the same age, I think, than Matteo. He just defended his PhD last year, 1 year ago, and was working 3 years with Stéphane Ballac and myself as advisors. To click, okay. So this is the plan of my talk. So there are 6 sections. So in the first one, I will state the problem from the mathematical side, going from physics to mathematical formulation. In section 2, I will give an example which is well known because it is the simplest possible example in this category of problems. And then in the third section, I will classify the problem that we can tackle, which are more general than those of section 2, and state the results and give a little hint about the way that it is proved in section 4. Then in section 5, I will show a way of computing the objects that we have studied from a theoretical point of view and conclude in section 6. So let us go to section 1. So the motivation is in optoelectronics, what is called a micro-resonator. So a micro-resonator is the union of 2 classes of objects, fibers or waveguides, which are in principle, in fine mathematical point of view, and in general straight. They don't have, they have a section, but other way they are straight, and they are coupled with each other by what is called micro cavities. This is a compact object, so this is bounded, a bounded object which has a structure and is often a shape which is radially symmetric. So you see on the slide rings. So of course the physical object is 3-dimensional, but it can be modelized by its section, this 2-dimensional section, and also computed. And so a way of investigating the properties of the union of these fibers and the cavity is to consider the cavity alone. And it is what we will do. And so we have an object which is bounded, which is dielectric. So I have an optical index which is different from the index 1 of the empty space around. And we are looking for its spectral properties. And now, of course, it is compact and in the free space, we will not find eigenvalues. We are in the world of resonances. And a special category of resonance, we will see that resonances, there are many and with different features. And a special category of them will be interesting for us. They are called the whispering gallery mode. From the mathematical point of view, this means that they are complex because they are scattering resonances, but very close to the real axis. So to go from physics to what we will study and compute, we start from the Maxwell equations. So I write here Maxwell equations in the 3D space, R3, with electric and magnetic fields. And here, the n of x is the optical index. So the optical index is a relative quantity. It's 1 in empty space, and it is larger than 1 in the cavity, bounded cavity. And we have what I wrote, outgoing radiation condition, and we will comment on this later on. So now we may consider the 3D formulation, but then we will assume that n is radially symmetric. So it's varying, if it varies, only in radial, with the radius. And for the 2D formulation, we will assume that so the 3D formulation, the cavity is a sphere, and in a 2D formulation, it's a cylinder, so that you may consider infinite or not. We will not discuss that. The important point is that here, the omega, the 2D, the 2D part, the section of the object is either a disk or possibly an annulus, and that n, the optical index, depends only on the radius. And then in the 2D formulation, we eliminate and don't consider any, the vertical coordinate. So now we have some ansatz. I don't pretend that from the 3D we will have everything. But what we are interested in, it's possible that we cannot find anything else, but it's not my purpose. So I take that as an ansatz. So we in 3D we look either for the electric field in the form of a curl of some scalar function multiplied by the vector, so it is a unit vector in the radial direction. It is a TE mode, or you require the same, but for the magnetic field. This will be the transverse magnetic, the TM. So this is very coherent. It is E formulation, H formulation. In 2D, it is swapped. So it is very confusing. And when we start studying that, we are completely mixing up the TM and the TE. Then the electric field is search for a scalar function multiplied by the vector, but in the z direction, and it is a TM. And for H, everything is swapped. And you see that here there is no dependency in Z. And the 2D can be phrased directly as scalar equations in U. So the advantage of this is to connect these equations with something else, with acoustics, for example. And you may recognize here standard Helmholz equation, but with multiplying the k square. So you are looking for couples U and K. K is the frequency, and it is the same than the, for example, the acoustics equation, where n is replaced by 1 over c, or where c is the velocity of sound. And you have the other form. So the Tm, you have this, so you don't have any perturbation in the Laplace. And for the other equation, you have the optical index, which is inside between the divergence and the gradient. And now, as everything, so the geometry and the index, they are all axisymmetric, then you may practice the separation of variables and obtain families of problems. So in 3D, you use the spherical harmonics. So here you have the angle, so the two angles, phi and theta. Here it is the part with the Legendre polynomials. And of course, in 2D, it is simpler. You have simply the radius and the angle and the polar part. And there is a way in the end, you obtain an equation which is written now. It's ordinary differential equation simply, and with some parameter which are quite innocent. So you have a parameter which depends on the dimension, and so it is 0 in 3D, 1 in 2D. It is not what you expect, but there is some change here, a change of function. And so in the end, you have a sort of Laplace operator. Here you have a centrifugal potential. You have minus Laplace, 1D Laplace. And here you have the, so the Q is a parameter which is large for more oscillating modes. And you have the part K, depending on the frequency in this in this part of the equation. So anyway, and so the P will be in plus or minus 1 depending on T and Tm, and of course swapped between 2D and 3D. So this is not very important. This is important when you have to connect that with computations or with physics. But for us, from the theoretical point of view, they all have about the same properties. So now, I will review this equation further. So now we have to explain what was not yet explained before, is that what we should put as outgoing radiation condition, the condition at infinity. Because if we don't put any condition at infinity, the problem is not well posed. We will not find anything. So we have essentially an Helmholtz outside. So the capital R is the radius of the object. So we have a disk or a sphere which has the radius R. So the R is the radius of the object. And N is varying for small r less than capital R, and beyond the capital R, it is 1. And so outside the object, the cavity, you are in the free space. And the equation in the free space, so when n is equal 1, you obtain simply that. You have your Laplace here, the centrifugal potential, and the spectral part. And now what we find often in the literature as the Sommerfeld condition for Helmholtz or Silver-Muller condition for Maxwell. But here we are looking for complex resonances, and we won't obtain anything on the real axis, and these conditions are not suitable. The solution of these are exponential waves that are either exponentially decreasing or exponentially increasing. So it's easy to understand if you don't have this potential and you have only the W, the derivative of W, then you have the standard exponential IKR, and when K is not real but complex, they are exponential increasing or decreasing. And now to understand what we want to have, we have to recall what is the mathematical definition of resonances. It is they are the poles of the extension of the resolvent of the operator. So the operator I'll call a K. So K is a spectral parameter, and so AK is a self-adjunct operator, and bounded from below, and its spectrum is R plus. It is and it is essential spectrum. It doesn't have any other spectrum. The resonances are understood like this. So the upper half plane with imaginary K positive is in the resolvent set. Then the resolvent, so the inverse of AK, is holomorphic. And the resonances are the poles of the extension of the resolvent as a meromorphic function between different space. Now, the extension of the resolvent has to act on much smaller space to be defined. For example, L2 is compact set. And with this information at hand, you see that when you are in the upper half plane, the among the two possible type of solutions that you have for the free space, you have to choose in the upper half plane that which is bounded and tends to 0. And in our case, with this centrifugal potential, it is the Hankel one. So you have to keep Hankel one when you extend to the lower half plane. So this is the reason why for the radiation condition, you have to impose that your solution is proportional to Hankel 1 with some Hankel 1 directly into D, and with 3D it is this function. Okay, so and you find this this term in some paper in physics, Sigurd condition. So it corresponds to the same thing. So now we have our problem completely well posed. For simplicity, we will consider dimension 2 with the transverse magnetic because it is the simplest way. So you have this equation, the Helmholz. So you are looking for U and K complex in the lower half plane, and with such a behavior at infinity. And by separation of variables, you have this family. So the parameter, the important parameter is the polar mode index, which is M. In Z, in N, it is the same because it is M squared. So it is a problem that we will talk about now. So a little bit of bibliography. So we have discussed this. So when N is constant, it is also the problem of scattering by convex transparent obstacle. And in this case, we know from the literature that there is existence of sequence of complex K with imaginary part negative, but with imaginary part that tends to zero super algebraically. So this means that they are whispering gallery mode. It is what we are looking for. So we want to study these guys in more detail. And it is in complete contrast with the scattering by a convex impenetrable obstacle, where the imaginary part of K stay away from the real axis, and even if I understand correctly, they behave that the third root of the real part. And there is a strip completely free of resonance. So I wrote here some papers among many others which are dealing with these problems. So I will talk about the constant index in disks, because there we have a way, almost analytic way of finding solutions. Because our equation, you see that now we have only one, the optical index is only, it is a constant N0 inside the disk, and it is one outside. So now this equation is the union of two equations. When it's less than the radius, then you have the N0 constant. At the radius, they have to match with each other in a simple, the function of the derivative, and outside it is Hankel 1. So we will find that inside this should be proportional to a Bessel function. So the Bessel function will tend to 0 at 0. And after that, you simply have to use a continuity. So with the continuity, you compute the coefficient of proportionality, and then you impose the second matching condition on the derivatives, and you find this equation where the ingredients are N0, of course, and the derivative, and so the Bessel on its derivative and the Hankel on its derivative. And the resonance that we are looking for are the roots, are the complex roots of this equation. simply. And now it's possible to compute by root finding, some root finding, the roots of this holomorphic equation. So this is an example of what can be computed. So there is some value of n. So the problem is that I cannot see the title of my slide because I have to keep this this thing. No, it is not possible to change the place of that. Okay, so I suppose that you see what are the parameters exactly. So each dot, each of these small dots correspond to one resonance. Here it is the real part, imaginary part. So of course it's just a little part of an infinite set. And the other way, so it is limited, it is bounded on real part, bounded in imaginary part, but also it's bounded in the value of the parameter. The parameter is varying from 0 to 60. And the color of the dot is, it corresponds to this color bar there. So the darker, very dark blue corresponds to small value of m. And when it tends to yellow, it tends to 60. If you increase, then you will have another slice there. And this will fill everything, but with larger values of m. And so you can see some structure. Here it seems to be a sort of lattice. And then they organize like lines. There is some empty space there. And there is something that you cannot see what it is. So you will see on the next slide. Yeah, here. So now it's a zoom. You see, you have the same extent in real part. And here, so it is my mail, sorry. And you see the structure above this limit. There is a limit. And here the limit is that quantity. And so this set is called the inner resonances, and the rest is the outer resonances. The inner resonances are living more inside the object, the outer are more outside. And indeed, it seems that the outside resonances resemble the resonances of the obstacle when you cannot enter at all in the object, in the dielectric object. So there is this, so the line, it is this equation for the value of n0 that I gave, it's minus 0.53, and you see that from the representation, it is exactly. Okay, so now we are interested more in this. It is what we will access from the theoretical point of view. So we have the polar mode index, so it is our parameter in the equation. And there is another one, which is an internal. And what you see, the branch here, it is not a branch in M because you see it is, the color is changing. It is a branch in J. So we have the same J, but with different M along this branch and another J. So it is J equals 0, J equals 1, 2, 3, and so on. And here you have a plot of the U of the function for the same value of N0, I suppose, and different value of M and different value of J. And you see that here J equals 0, you don't have any oscillation inside. So you see the disk here, the radius of the disk. And M, when M gets larger, then the U is concentrating more closer to the boundary, but inside. And if M is smaller, it is radiating more outside. And for J equals 1, you see that there is an oscillation inside. J equals 2, you have two oscillation, and this same sort of structure. So in the literature, it is a journal of optics, of Optical Society. You find an asymptotic formula, and it is a sort of model what we want to have, but in a much more general setting. And the proof relies on asymptotic expansion of special functions. They started from the equation from which we had to find the roots, and studied the special functions to asymptotics where M is large of Bessel and Hankel to find this sort of expansion. So here K is a resonance, M is a parameter, so the polar mode index, J is the internal parameter corresponding to the number of oscillation in radial oscillation. The main term is M divided by R in 0. Then you have an expansion starting from 1, and so they all start from the same value, and then they are discriminated by this J, and starting with powers of 2 over M at 1/3, and the integer multiples of that quantity. So you see it is an asymptotics when M is larger. And here you have this AJ, which are the zeros of the reverse function, and some formulas. So now we go to our more general case, and what happened is that our 1D family of functions is equivalent to a Schrödinger equation, a 1D Schrödinger equation. So it is very easy to see. So I write again my ODE, the differential part, the potential part, and the spectral part. You divide by M square, N square. So N is a function. You multiply by the left, and you obtain that. So here you have something which is a potential. So the potential V of R is the effective potential. It is simply 1 divided by the optical index and R square. The spectral part, you just set E K square on M square, and this is the energy. So an eigenvalue now is like an eigenvalue. And then you have 1 over M square. Of course, you set H 1 over M, and then you have a semi-classical parameter H, which will tend to 0. And your equation is completely equivalent to that one. So 1D Laplace multiplied by H square, a potential, and the energy. And now we are looking for the resonances of this equation when H tends to 0. Now we have to understand how is varying the potential. And so the potential have some discontinuity in general. So you see there is there is a special point which is the boundary of the disk, so with the R, and where you may have a well at that time, a minimum. And you can compute the derivative of course of the potential at that point. It will be more clear on this slide. I will explain on the figure. So here you have so R is 1. So it is the abscissa of the variable small r here. You have the optical index. It is the case of when it is constant. So it is 1 when we are larger than 1, and it is 1.5 in the object. So for small r smaller than capital R. The potential is 1 divided by r square. So it is that branch. And here it is 1 divided by n0 square r square. And n0 is larger than 1. So you are deeper there. And you see that here you have the well, the bottom of the well, and you have a half triangular or step linear well at the limit of the object of capital R. Now, as we consider varying indices, so my example is exactly this one, which was considered in a paper in physics by Ilchenko et al. So when delta is 0, we have the constant. When delta is 2, we are exactly in that situation. Now you see we have something which is variable, but here we have still a minimum at the same place, but now the derivative, so this tonic kappa, is 0. And the second derivative of V has the correct sign to have a half quadratic or step harmonic well at that point. And for the last one, the delta is taken larger, then the kappa is negative, and so we don't have any minimum at that place, but we have a minimum further inside, and which is a standard harmonic well inside. So these are our 3 cases that we will talk about now. Now I will simply show some simulations that have been done to see how a first mode, so in this this family may look like. They are not completely exactly the same, but they are in the same family. So you see that it is the same shape, so it's constant, and so it is a potential, the effective potential there, and here you have the real part with some normalization of the first mode, mode of the family that we are looking for m equals 60. And you see that it is strongly confined in the bottom of the well. It is not very, very strong because 60 is not a very large number, but still it is confined. It is very, very small outside. And for a 2D plot, you see that now you may count by yourself. You will find 60 oscillations, and inside, so you have the maximum. You see it is the profile is maximum at that place, and here it is maximum all around and radiating gently outside. Now the second example, when you have this half quadratic, you see that the mode is larger, so the other parameters are exactly the same. And when you look at the 2D plot, you see that it is a little bit away from the boundary of the disk and leaving a little more inside. And for the third case, now we are completely inside. You see now that the minimum is not at the boundary, but there. And now you have the 2D representation where you are much more inside. Okay, so now I will just tell what we did with no technical details because it will be too long and too difficult to explain and remotely also. And I prefer to address a little bit of numerics. So I repeat here the potential, this quantity, which is a sort of adimensional, it is an adimensional curvature. So the adimensional curvature, if the n is constant, the index, optical index is constant, would be 1. And n1 is the derivative at the boundary of the cavity of the index. So you see that if it is constant, then this term disappears. And it is the so the effective sort of effective curvature. We found this expression, also effective curvature, in a book, old book by Babbage and Bouldirev, where they addressed whispering gallery mode for Dirichlet, for the Dirichlet problem, for Dirichlet eigenvalues. So the case A is that the model is at the half triangular well. You have, so it is the caricature of the potential when you take the first term in the Taylor expansion, the first non-zero term in the Taylor expansion. So you have a constant outside and this absolute value, the modulus of R minus R here. And in the case B, when the derivative is 0 and the Hessian has the correct sign, then you obtain the half parabola. And for these two situations, what we are doing, so now we construct. So it is a construction of quasi-pairs. So it is the first step of the whole study that you construct quasi-pairs. That means that you construct approximate solutions. So you construct the W, so underline, it is underlined because these objects are not exact objects, and we will see in what sense they can be considered as an approximation of exact objects. So the game is to construct families of quasi-pairs with this underlying small parameter, which correspond to large M. And we are doing construction in the bottom of the well. And then, so I describe a little bit in these two cases, A and B, and then it is this multi-scale analysis where you construct solution on the left and on the right with the correct scales, so that the equation, so no, the equation is not there. So the equation is there. So that the equation is in a certain sense homogenized. You homogenize the L and the V close to the bottom, and the homogenization gives different powers. So outside you obtain the scale the abscissa is divided by h, but on the part where the potential is starting from its minimum, for case A, you obtain at the first term correspond to an airy function with the scale abscissa divided by h to the 2/3. And in case B, this will be Hermite functions, and at scale abscissa divided by h to the 1/2. So we study separately each side, and we match them by the continuity of function and derivative. And of course, in the other case, when n the jump is inside inside the operator, then you have some n of r arriving there. But it is exactly the same principle. So the formulas are not the same, but the nature of formula is the same, exactly. And the outcome, so I gave you the first term that we found, and this construction can be pursued as long as you want. It gets to infinity. So for half triangular well, then here we don't have so many terms, so we don't see any difference with the formula of the physicist. But when you go further, you will see that so you have a difference, because here you have this term, you have the kappa, and for them they have only the one at this place. So they are different. They are different because, but they are not new terms. But the coefficient there is different. So in case B, now you see there is no 1/3 or 2/3 anymore. You have something coming from the harmonic oscillator. And when you have an internal quadratic well, then it has a similar nature with a new radius, because an internal radius. And coefficient slightly different, because here you have it is only half harmonic, then fully harmonic. So it is the first terms of the formula that we obtain by our construction. Of course, we have also formulas, representation for the modes, for quasimodes. And then how to conclude from that? So the step one. So I describe rapidly what is the step one, the construction. So it is a construction which goes as far as we want. It is an infinite process. Then from the infinite process, which is asymptotic construction, we have to figure that there are some C infinity functions underlying, and this is the Borel summation trick. So this k of j, the underlying k of j, that depending on m is not a C infinity function of m. It is a C infinity. It can be viewed as a C infinity function of a negative power of m. So the negative power will be, of course, 1/3 in case A, and 1/2 in the case 2, B and C. And so there, behind the object that we construct step by step, there are C infinity functions whose realization give the quasimode. And when you have that, then, which still more work, you can see that you enter in the framework of what is called the black box scattering. And black box is a very good name because you don't have to understand the details of the proofs. You have only to understand what are the statements. And for us, it was not completely easy. But still, we have understood why our examples, our framework enter this very general thing and applies. So the outcome is the following theorem. For each of our constructed family, for each J and M, we know that there is a true resonance which is super algebraically close with respect to M. Well, it is not uniform in J, but for each J, you have M of M minus infinity. So this O depends on J. Okay, so let us go rapidly to numerics. So I wrote again the equation, the condition at infinity, and the problem is that the condition at infinity is not suitable at all for numerics. Because you are choosing the function that is exponentially increasing. But there is this very famous perfectly matched layer, which is just the optimal solution to the problem. And indeed, the trick is to not to leave the R. So R is a physical abscissa, it is real. But now the trick is to it is the back. It is we travel back to the upper half plane now. And indeed, outside the object, so for the small r larger than the capital R, you are in a region where your equation, which the solution of which is this Hankel one, is still valid. So when R is complex, the equation is still valid. So now the idea will be to follow a path in the complex plane outside the object, so that to come back in a region where you are, as in the resolvent set, the H1 tends to 0 and the H2 blows up. And this can be done in a very simple way. You choose a path so that in the object you do nothing. So you see your R now is complex. The parameter of the path is real. It will be on still R plus. You multiply it by 1 plus something which is purely imaginary. You do nothing while you are in the object, and you give some region where you can adjust, and outside this region, beyond some RPML, you are with imaginary the I multiplied by some sigma 0 positive that you have to choose. It is a parameter of the method. And in between, the simplest way is to do that. You choose an affine function linking this and that part. Usually, what people are doing is that they extend this region where you do nothing beyond the R. And so they have this affine part a little bit pushed away from R. So I will show you the effect of doing that. So now it is simply apply a very well-known formula, the derivative of composed functions. Indeed, it is something very simple, but I find it difficult to understand deeply. What is it? It is like a trick, but you may understand what is behind this trick. And in the end, you have so the original problem, the transformed problem that is equivalent. And now what is interesting is that you may discriminate now if you have followed your path and go back to the upper half plane, then you can discriminate H1 from H2 by telling that H1 tends to 0 and H2 is blowing up. And now you may discretize your equation by considering a bounded domain and putting a Dirichlet condition at the boundary of the domain. So we will take as boundary the same as when you are just out of the layer. And then so we first as we have a very powerful and versatile code in finite elements, we did also computations for 2D objects. For 1D it is also possible, but one of the other advisor was more at ease with finite differences and started writing a code with finite differences. So at first I was not very happy with that because, but when starting to play with it, I was convinced, because we are in 1D, and then the features, it has very interesting feature. So it is easy to code. You don't need to have a full library. So it is written in Octave MATLAB. So it would be also possible to write that in other more fashionable language as Python or Julia or so on. But it is quite easy to code, because you see you have to code your coefficients, and the matrices are sparse. So if you do a finite element with degree 1, you obtain almost the same. The rigidity is the same than if you are doing a P1 element. Mass is diagonal. It is the condensation, the mass condensation of what you would obtain with by finite element of degree 1. So the matrices are sparse. And the discontinuous coefficient in the operator or in any other part is not a problem. You simply have to pay attention that you have a node at your discontinuity point. Anyway, it works, but it is so it computes rapidly. And if you want to have this feature, and for me, it was very interesting to discover that the convergence. So if you have the nodes are your discontinuity points, the convergence is very regular. So it is a spectral problem. So it converges as the square of the small parameter of the method, and then you can extrapolate. And you may have error estimates, and this is very, very precise and efficient. And you may also have integrated post-processing, and when you compute, decide from the computation if it is an inner mode, outer mode, or spurious. Spurious is the solution that you obtain from the numerics that are linked with the method, the PML method, and don't represent any correct resonance. And it is also to have to follow some parametric study. So with computing 2 seconds, you may have 50 resonance with 10 to the minus 8 relative error, computing 25 whispering gallery mode. This is a typical thing. So let us go now to some numeric examples. I am also so here so there is some values of so I have to give some m, some r, some and 0. Also the code will propose some parameter for the computations. You have to choose how many nodes you had. So it is done with 10,000, and then the code is computing 1,000. Then it computes 2,000 and 4,000. And then change a little bit the sigma 0 to identify what is the structure of the modes. And the outcome is that here in blue, you have the modes that have been identified as inner, or those are outer, and those are spurious. And the numbers is the order in which they are listed. So with the numbers, you may identify them and plot the result. So you see that here it is the full. You compute 50, you obtain this. Then it is a zoom on those you are more interested in are the inner mode, and you see that it is not the same scale. It's the real part, imaginary part. So the scale is smaller, and you have this pattern for the for this mode. And so the whispering are those, and this branch is going to the to the limit at infinity of minus 50 or 53. And here are some modes. So the one is this guy, so very close to the. It is the guy which is completely concentrated on with only one oscillation. The number 7. So number 7 is a spurious. It is there, number 7, and you see that it numerical problem, but nothing to do with the continuous problem. So number 8 is this one. So it is an outer mode, and you see that it is a little bit inside, but it is mainly outside, and it is damped because it is damped by the perfectly matched layer. And this one is a number 22. I think that it is this one, and it is inside, but it is radiating outside. So here it is damped by the layer, the numerical layer. But if you match here with the radiating, with the H1 not damped, you obtain this. So you see that it is strongly radiating outside. Okay, so this is for another example. So this was TM, this is TE. What I want to show rapidly is the effect of introducing an R1. So the R1 was this, to extend the region where you do nothing. You start the PML further. And so you see what happens if you have this R1 larger. So it was here. So I don't. R1 is 12. So you see, you have much more spurious. And then when you increase, the spurious are closer and closer to what you want to compute. this means that it's much less precise. And here it is an example of what you compute with this largest possible. The layer is abutting the object, and then so in principle you compute the same thing. You can see that it is when you stick that with the radiation, you obtain exactly the same thing, but here the error indicator is to the 10 to the minus 11, and here it is 10 to the minus 2. So here I followed, I did some parametric study. If you have an annulus that is thinner and thinner, so you see, so it is the profile of the optical index if the annulus has this width. And getting thinner and thinner. So these are 3 examples, but I need for all these values, it is 100 values different, and these are the real part. So this is the real part of the first the first mode, the first whispering gallery mode. So it is the real part. The second one, the real parts, and the third one. And here you see the imaginary parts. So the blue corresponds to this one, to the first one, the red, the second one, and the black, the third one. And you see that it was a sort of surprise for me that the real part seem to converge to some limiting value. What was not a surprise is that the imaginary parts tend to minus infinity when the thickness is tends to 0. That so it is possible to compute this. So so here I rehash a little bit what I have done. So what I want to say is that according to the value of the parameter, if the parameter is in between, not too small or not too large, then you have some region where the 2 studies, numeric and asymptotic, give according results. If the M is very, very large, then the computation will have problems because you have a problem which is too stiff. But if it is too small, then the asymptotics, of course, will not give any reliable result, or they are not precise at all. And the most annoying thing concerning the asymptotics is that they don't give any information about the imaginary part. But numerics does that very, very precisely. And so my conclusion is there. For us, for the moment, we have some guess. So we can see that the behavior of the imaginary part is exponentially decreasing when m tends to infinity. We could figure that perhaps there is a formula like that, like it is in Elfer and Justran, puis dans Lille, but it's for analytic potentials, and we have no idea if a proof is available for us in that in such a case. So I think that so it is the reference of our work, so the thesis by Zois, a paper which is published, a paper in revision, and a paper and code in preparation. And thank you for your attention with an image of something that some landscape that we hope to see again after the end of our second lockdown tomorrow. Tomorrow is the end of our second lockdown in France.
Thank you very much for your talk.
I was a little bit longer. I have to apologize for this.
Thank you very much. Are there any questions for Monique?
Could I ask a quick question?
Yes.
About the spurious resonances. So, if I understood correctly, these are not spurious resonances in the same sense that, say, spectral pollution might occur. These are rather spurious resonances which are perhaps the result of the fact that the problem is ill-conditioned and you don't have God's computer with an infinite precision arithmetic. Is that correct?
No. In fact, the spurious, I don't know, perhaps spurious is not the good term for that. Indeed, if you consider as exact problem, this problem, then all the eigenvalues, now you compute eigenvalues of that, all eigenvalues are correctly computed, but they have to be interpreted after that. And those, you see that they have a structure, and indeed they are the shadow of the essential spectrum of this problem. You see, this problem is an unbounded domain. It is on R+. And it has an essential spectrum, which is a half line in the complex plane. It is the half line is turned from an angle corresponding to the sigma 0. And what you are seeing here is the bounded realization of that. You see.
Sure. I understand. Yeah. So they're not really spurious. They're genuine because, well, yes, somebody has to have the job of approximating the essential spectrum.
Yeah. So you are correct. Spurious is probably not the good term for that. They don't represent resonance of our problem. They represent something else. They are eigenvalues, because now it is a problem. It is a non-self-adjoint problem. So it is very fascinating, because you start from a problem that is self-adjoint, then you extend the resolvent, and you have the equivalence with a problem which is well posed as spectral problem, but it is no more self-adjoint because it has complex coefficients and complex at infinity. It is not the perturbation of a self-adjoint problem. It is a genuine, deeply non-self-adjoint problem. And now after that, there is a cutoff somewhere. So now it is bounded, and then it is discretized. So we have, it is discretized by these finite differences. But you are correct that they are not spurious created by some deficiency of the numerical method.
Thanks. Thank you.
Any more questions? Okay, if not, let's thank the speaker again and postpone further discussion to the informal.